Hi, I'm Will Crichton, an assistant professor at Brown University, and this talk is about how I use Rust to make a data analytics program 180,000 times faster than my initial Python code. But more generally, this talk is a case study on the different tools in the Performance Engineers Toolkit. So for context, I was running an experiment where we asked people quiz questions in an online textbook like this. So we had a set of readers and a set of questions. Not all readers answered every question. So we had a sparse set of responses for each question, either 1 for correct or 0 for incorrect. And you can think about this data as like a table with missing entries. So each row is a person, each column is a question, and each cell is either 0, 1, or a blank for no answer. That's the raw data. And my research question was about determining which questions best tested people's abilities. And one way to do that is by analyzing each question's discrimination, which works like this. So first, we compute each reader's average score. Then, for each question, we pair up a reader's individual score against their average score. Then we compute the correlation between these pairs. And the idea is that a higher correlation means higher discrimination, a more interesting question. Now, this quantity isn't too difficult to compute per question, but what I wanted to know was that for some size k, what subset of k questions has the highest discrimination? So here's the rough pseudocode for how to compute that quantity. We have this function, k core set, which takes the data and a size k. And then for every k-sized subset of questions, QS in data, we compute the set US of all users that answered each of the questions QS. We compute the correlation of the users' answers to QS with their answers on everything. And finally, return the questions with the highest correlation R. So for example, if k was 2, then it would look like this. We get each subset of size 2, compute the correlation for that subset, and then get the highest scoring subset. So that was my research question. And I'm going to talk through how I iteratively optimized my implementation of this algorithm. Now, the first step should always be implement the simplest possible version first. Now, there's two reasons for this. One is that if the simplest version is fast enough, well, you're good. I mean, there's no need to optimize or do anything more complicated. But two, if you do need to optimize, then now you have a reference solution you can compare for correctness as your optimizations get more involved. So starting with the pseudocode on the top, I implemented a straightforward Python function using the pandas library. The details are not particularly important, just that the Python code is pretty similar to the pseudocode. But what I quickly found was that the Python code would take 3 years to finish on my data on my laptop at the value k equals 5. So that gave me a performance problem to solve. Now, where do we go from here? Well, a common response might be, let's improve the big O, like maybe we'll go from O of n squared to n log n or whatever it is. But constant factors matter, and for this talk, we're going to stick with the brute force approach, which is actually exponential, and still find a 180,000 times speed up. So instead, we need to start by picking a more suitable language for the task. Python is not a great programming language for doing performance engineering, which is not to say you can't optimize Python code, but it's going to be a lot easier if you use a language that gives you reliable control over data, like how data is laid out in memory and when it gets deallocated. My preferred language for performance engineering is Rust. So our next step is to translate the Python code into Rust. And here's what that code looks like. So we define a user and a question type, which are just aliases for strings. And then a row in our dataset contains a user, a question, and a numeric score, which again is just 1 or 0. The k core set function then takes as input a collection of rows and a number k, returning the vector of questions with the highest discrimination. And if you think about these rows like a database, then the opening part of this function generates indexes for efficient lookup. This only happens once before the inner loop, so its performance isn't particularly important. We just need to focus on the data types involved. So this variable q_score has type hashmap from question to hashmap from user to u32. This lets us look up the scores for a given question and a given user. Then all grand totals maps from a user to u32, which is the total score for that given user. Now here's the main part of the code. So we start by getting an iterator of all the questions. Then we use a helper function to generate all combinations of questions of size k. For each of those combinations, QS, we say for each pair of user and their grand total, we get the sum of the user's scores to all the questions in QS, returning none if they haven't answered one of the questions. Then we get back a pair of their total on the subset and their grand total, and compute the correlation between those two vectors. And finally, we get the maximum of those correlations. So with this basic translation of Python into Rust, we end up with an 8.5x speedup. So what this graph is showing is on the x-axis is each performance optimization step. And then the y-axis is the relative speedup to Python on a logarithmic scale. So Python starts at 1x relative to itself, and then Rust is at 8.5. Or another way to say this is that Python would take 2.8 years to finish on our particular configuration, and the initial Rust code would take 124 days. So we clearly benefited from the translation, but it's worth observing that 8.5 is not 180,000. More generally, using a systems language does not automatically give you maximum speedup. I think there's kind of a myth that some languages are inherently fast and some languages are inherently slow. But that does a disservice to the role of the programmer in using those languages effectively or not. The key thing now is that by working in Rust, we have the foundation for both understanding our performance bottlenecks and making surgical and predictable changes to improve those bottlenecks. So then, rather than guessing where our bottlenecks are, we should start by using the foundational tool in the Performance Engineer's Toolkit, a profiler. So I ran my profiler, Samply, on the Rust code and got back this profile. Now, this is a lot of information, but if you dig through the call stack, you'll find that the inner loop of the function spends most of its time, 50%, in hash map get. Now, that seems like too much time spent hashing. We might expect to spend most of our time computing correlations. But no, it's all in the data structure. Specifically, this corresponds to the highlighted expression where, given a question and a user, we look up the score of the user on that question. The problem is that this involves hashing two strings, which have 36 characters each. And so we can solve this problem by trying to hash something a lot smaller. The idea is that we want to convert these big strings into cheap integers, and we can do that by assigning each string a unique index. So first we pull out the question strings and user strings into lists of unique strings. Then we copy over the hash map. We get the index of each string in its list, and then replace the strings with those indices. That's the basic idea. Now we have a hash map over cheap numbers rather than expensive strings. And here's roughly what that looks like in code. So first, we define a type for the values being indexed, the type of references to questions. And then I'll use some helper macros and functions to define these numeric indexes. So we create this type question IDX, which internally is a 16-bit unsigned integer. And once we have those types, then we create the domain of questions and users. That's the two lists in the top right. And then to create this hash map, we're going to change our data structure, Q to score, that used to be a hash map from a question, the string, to a hash map from the user, also a string, to U32. And we'll replace those types with a different type. So now it's a hash map from the index to the hash map of the index to the U32. And that's about all we have to change. Once we do that, and we're hashing this cheaper data type, our code is now 4 times faster than before, just because we're spending less time hashing. And so one lesson here is that sometimes adding a layer of indirection can make your code faster, not slower. By dealing with this cheap proxy type, our inner loop gets 4 times faster. But another subtler lesson is that good abstractions should prevent bugs without hurting performance. So for example, let's say I didn't define those custom types, and instead I just used unsigned integers, a U16 everywhere. Then I could accidentally use a user index where I should have used a question index. Now, at best, this will cause a runtime error, like an out of bounds. But maybe my script just produces the wrong answer, and that's really scary. However, if I use a more typed approach, then these kinds of errors get caught by the compiler. So if I use a user index where it expects a question index, that's immediately flagged and the program can't even run. All right, so performance-wise, this is an improvement, but we're still spending a lot of time in the hash function, even if it's just hashing integers. So that raises the question, can we get rid of hashes altogether? So remember, this is what our data currently looks like. We have questions, users, and this nested hash map keyed on the indices into those lists. And the reason we used hash maps in the first place is because our data is sparse. Not all users answered all questions. Hash maps are one representation of sparsity, but we can choose others as well. So one possibility is to use a sparse matrix format, which looks like the table with holes that I showed you earlier. So each row is a question and each column is a user. Each entry is 0, 1, or a hole. And the advantage of this representation is that given a user and a question, I can directly look up the score without doing any hashing. So what does this look like in code? Well, the simplest thing to use is a vector of an option of a U32. But again, this is not well typed. We could index those vectors with any old numbers. So instead, we will use a special index vec, which is internally just a vector, but it can only be indexed by values of some type I. So we'll define this alias question vec, which is a vector of something indexed by questions. Similarly for users, and then we can define, taking our old Q to score type, replace it with a new one. Instead of a hash map now, we have a question vec of a user vec of an option of a U32. And again, the rest of the code looks roughly the same, but now we are doing a more efficient lookup. And once we do that, our code gets 5.7 times faster. So we're doing pretty well. We're already down to only 5.3 days to finish executing this big computation. But the general lesson here is that runtime efficiency often trades off against memory consumption. Like before, we had a maximally compact data structure, this hash map. But once we use the matrix with holes approach, we have to use more memory to store the holes in exchange for efficient indexing. Now that trade-off is worth it here because we don't have so many holes that it would take up all of our memory, but weighing that trade-off is part of performance engineering. And speaking of trade-offs, we do need to talk about safety. So when we're indexing into this vector data structure here, like when we do Q to score, star Q brackets U, by default, those index operations are bounds checked, at least in Rust. Now, those checks incur a small but still observable cost. So we can slightly optimize our program by using a non-bounds checked operation, assuming we've very carefully vetted our code for correctness. The result of this is that this produces a 16% improvement in performance, which is not huge compared to our previous optimizations, but it's sizable enough to mention. So the lesson here being, Runtime safety checks come at a small but noticeable cost. We do sometimes need to trade off safety for performance if we can't ensure safety at compile time. All right, so we've gone pretty far making tweaks to the same core computation. But to go farther, we need to rethink how we're organizing the program. So this is what our very inner loop looks like in pseudocode. Given a set of questions QS, we compute the scores of users who answered all the questions in QS. But the problem is that we're doing a lot of wasted work here. Like in our data set, only a small fraction of users have answered all the questions in a given subset. And so an alternative possibility is to first identify all the users who answered the questions, and then unconditionally iterate over just those users. This not only removes a source of branching, which can be expensive for CPUs, but also we can compute the subset of users in a more efficient way. So again, here's the idea. We started off with a string keyed hash map, and then we converted to this index keyed hash map. We converted that to an index keyed vector. And then the final step is to add another data structure, which is a member set to each vector. So this member set describes which indices in the vector are filled with data. So if we want to answer a question like, which users answered both question 1 and question 2? Then we can take the two member sets, intersect them, and produce the answer of index 1, in this case, user 2. So that's the high-level idea. And in the code, it looks concretely like this. So like before, we have this index set data structure, which is parameterized by our index. So a user set is a set of user indices. And then our queue to score data structure now contains both the user set and the user vec of scores. Now in the inner loop, for a given set of questions QS, we first start by computing the intersection of all the user sets. So this gives us just the users that answered every question in the subset QS. And then when we iterate over that final set, we no longer need to account for the possibility that a user didn't answer a question. So this works, but a key part of this optimization has to do with how the index set is implemented. Because our sets sort of platonically look like this. We write down brace 0, 1, end brace, but that's not how it actually is represented in the computer. If we represent the set as a hash set, for example, well, that's normally just a hash map where the keys are the members and the values are some dummy value. So if we intersect two hash sets, we still have to do lots of hashing. It's not cheap. But instead, in our use case, we can use what's called a bit set. So the idea of a bit set is that there's exactly 3 things that could be part of the set. And I represent whether that thing is in the set with a 0 or a 1 at a particular bit. So if my bit set could contain the numbers 0, 1, or 2, then that's represented as a 3-bit number. And the beauty of this approach is that intersecting it is as simple as bitwise AND. That is a primitive operation on most CPUs, so it runs very fast. Therefore, once we implement this whole strategy, our approach is 3.4 times faster than before. Pretty cool. And the lesson here is you want to move your control flow into your data structures. Like if you're really hyper optimizing something, every conditional is expensive. You want straight line code as much as possible. And I'll show you a good example of a benefit of this. Like the bit set approach is faster, but it's not hugely faster. But it exposes a good opportunity. Like if we look more carefully, our bit sets are not actually individual numbers, but lists of numbers. If your set could contain up to 65 elements, then our bit set needs to contain at least 2 64-bit integers. So if we want to intersect 2 bit sets, we currently do that by intersecting each pair of numbers individually. That's the sort of default implementation. But most processors contain what's called SIMD instructions that let you do things like a bitwise AND on multiple pairs of numbers at a time. And so if you optimize your bitset implementation to use SIMD, then at least on my particular processor's architecture, it becomes 34 times faster than without the SIMD. So that's pretty cool. And at this point, we are 26,000 times faster than our Python baseline and 3,000 times faster than our Rust baseline. That's the power of performance engineering. Now, I didn't have time to cover everything. The main thing I left out is parallelism. We can divide the work over each core, and on my 10-core MacBook, I get about an additional 10x speed up from that. If you want to read about that or any other gory details, you can check out the post that inspired this talk at the link on the slide. But really, what I hope is that you take away these 10 lessons that I believe characterize the essential concepts in the Performance Engineer's Toolkit. So thanks for listening, and good luck writing some fast code.